would like to introduce Dr. Jerry Jones.
All right.
And I have to give Jerry a tremendous amount of credit for putting this together. He's done a lot of work. He's kind of taken this advanced technology theme that we're doing this year and taken the ball and run with it. He's going to be our first presenter, our keynote speaker, and he will be introducing the speakers. So at this time, Jerry.
Hey, you want me to read your bio?
I don't think we have enough time.
Jerry's a very famous guy. I ain't kidding. He looks like an Okie, and he is. He's a very famous guy. I'm an Okie.
Yes, I know.
Jerry's been doing a lot of work with Ford, ITW, the Navy. I remember when he was doing his graduate work with the electroslag welding.
Yeah,
you know,
long time ago.
that was a long time ago.
Well, not that long.
Seems like yesterday.
I won't say that, Jerry. Anyway, it's a great honor to have Jerry here. He is well respected in the industry. I mean, way up here. Way up there. So, Jerry,
I
floor
can't live up to all that.
damn well better.
Bob gave me all the credit for this, and it's not mine. I sort of sat in the chair and pointed to all the places other people had to do things to make it all work. So welcome everyone. I'm.
Can you sit down with that leg? You had to go to the doctor, didn't you?
Yeah, I dropped something on my foot last night, so I was at St. Anthony's until about 10 o'clock. But anyway, I'm good. Everything's good. So I'm gonna sort of kick things off and talk about advanced technology, and I'm not going to cover everything because the other talks this morning are going to cover some things, and you'll find right outside here, as Jesse alluded to, the demonstrations. We brought in some pretty interesting things in welding, and kind of the nice thing about it is all of them at one time or another had their roots in Colorado, so that's kind of a plus for us here. So let me get started if I can figure out which button to push here. I may have to put my glasses on to figure it out. Hey Mark, where's your page down? Oh, there we are. Good. So, advanced welding, robotics, and processes here at the Rocky Mountain Welding Symposium, and I'm going to start out talking mostly about things that we've done or things that we've been involved in, and then I'll let the other speakers talk about the things that they've been doing. So I'm going to start out with this new process that we call high deposition welding. Officially, it's going to, I think, be hybrid induction arc welding, but until we get the first one in production, which we're starting on right now, AWS won't give it an official name. So we're calling it high dep because we started out with it being high deposition. So induction hybrid arc welding might be the title of it. What we do is we put a very high power induction coil in front of the torch, and then run it just like an ordinary welding process. But we have two independently controllable, equal power heat sources now, which completely changes our ability to do things to the thermal profile of the weld that we could never do with an arc. So the sort of advantages of this I'll talk about here as we go forward. But I'm going to talk just about the basics of the process, butt joint welding with it, fillet joint welding with it, and another little benefit that comes along with it that I'll explain later. So if we look at the process, basically, one of the biggest advantages is that we may, for all the applications we essentially have completely eliminated weld distortion with this process. So when we made the first weld, which was back in 2011, somebody noticed that the plates were sitting flat on the floor, that there was no weld distortion there. We created the process so we could go faster because we needed an application, but we've sort of been exploiting this, and it's been sort of the hallmark of it. So we typically have travel speeds in the range of 4 to 8 feet per minute. We can actually go faster than that. Single pass on 3/4 inch butt weld joints. We don't require any beveling or joint preparation. We just use a square butt joint with a fairly small opening. Flame cut plate edges, we don't have to do any special preparation to it. The total capital cost is about 2 times what a standard arc welding system would cost. But when you compare it to the other process that's out there right now that's giving us low distortion welds, which is laser hybrid arc welding, there's no comparison in terms of capital cost. The laser is just amazingly expensive compared to this process. So the operating cost, for the most part, because we can go faster, is actually less than for standard arc welding. It uses all the equipment. All the equipment that we're using is already existing in most major fabrication shops. So it's not like having to go out and buy a laser and learn how to run it and maintain it and that sort of thing. And we can make it portable. So, and you'll see the equipment out here that we can use to make it portable. So the project that we've been working on to develop it was funded by the Navy. and if you start looking at the total cost in terms of both the straightening that they have to do as well as scheduling problems that come up from it, fit up problems that come from it, and so forth, that's about the annual cost to the Navy of weld distortion. So if we can get rid of a significant amount of that, we can save a tremendous amount of money in the Navy. So here's a panel line with butt welds on a flat panel, and you can see how bent it is from the distortion. The other part is, and I didn't bring a laser, so I'll go over here and point at it. If you look at how they make decks to keep the weight down, they'll have a deck plate and they'll weld T-stiffeners underneath it. And where those T-stiffeners are welded, you get weld distortion, and that causes the deck to dip down like this. And you can see this in the picture. There's a T-stiffener welded under this deck here, and one here, and you can see the big gap underneath that straight edge. So those are the kinds of problems that we have in the Navy, and certainly in a lot of heavy fabrication applications that are due to distortion problems. So Miller did a little work on this at first when we started looking at it, and they got us a kind of a nice video there of what just the heating from the induction looks like. And I think it's important to note, I know you can't read the scale there, but we are actually bringing the surfaces of the weld up to the melting point before the arc ever even gets there. So that's really a key point to the process. So if you look at conventional welding, where it's on a fairly thick material, we're going to have to make a V groove so we can get the joint, get the torch down in there. Although Eric later on this morning is going to be talking about a new really cool process for not having to do that. But if you look at cutting the bevel and then making the various weld passes to produce it, we were looking at this, and the total preparation time plus welding time is about 2 hours and 4 minutes to make a 40-foot weld. With this new process, the high depth process, we're single pass, don't have to cut any bevels, don't have to make all those other passes, and so we're actually 8 minutes total preparation time and welding time. And this is what we were after, because what we're trying to do is build the world's tallest wind tower. And wind tower structures are such that to go taller, they have to get bigger around. And if you've seen any of these things being transported on the highway, we're done. We can't make them any bigger around and still transport them. So the key was, the key is to make a portable, automated fabrication facility that can actually fabricate the towers on site and move from wind farm to wind farm. In order to do that, to make it automated like an auto assembly line, we had a cycle time that we had to meet in order to be economically viable. And I have to make that 40-foot weld, including putting the plate in position, making the weld, getting it set up for the next plate to come in. I have to do that in 15 minutes. So I've got to make a 40-foot long seam weld in 3/4 inch thick steel plate in 8 minutes. I have to do that. So that was the reason why we invented the process and why we call it the high deposition process, because that's what we wanted from it. But so this really has quite an improvement over submerged arc, for example. And if we compare it to the laser hybrid arc welding system, there's just really no comparison. I mean, it's just outrageously expensive compared to what we're doing. Yep?
I gotta ask, is the same as the distortion level, like almost zero aluminum and aluminum?
We haven't done aluminum yet. We're still on steel. So I can't tell you what aluminum will do, but aluminum can be heated with induction, so theoretically we can do exactly the same thing with aluminum we can with steel. The Navy is starting to make some superstructures on the ships out of aluminum, but almost everything right now is steel, so that's what we've concentrated on. Yes?
Which part more contributes to the penetration of the weld?
We've got some heat flow modeling that we've been doing, but I'm not sure we have all the answers for that yet. The arc probably does most of the work near the bottom of the joint, because there is the induction is an electromagnetic field which dissipates as it goes down into the material. So it probably heats the joint a little more on the top, and the arc heats the material a little bit more on the bottom, but it's a very even heating from top to bottom. So if we basically look, that was our first robot back in 2011, set up to run those weld joints. That was our first 40-foot weld that we made back then. Not a bad looking joint, actually. This was it running at our wind site, actually welding 40-foot tower section plates together out in Oklahoma. This is kind of an interesting experiment that Miller did. They said, well, let's make a weld with this process, and then let's turn off the induction and see how much difference it made. Well, obviously the one on the left was made with the induction on, and the one on the right was made with the induction off. So clearly it made a big difference. So basically what happens with distortion is that when you use traditional arc welding, the arc is a giant heat radiator. So everything that's closer to the arc gets hotter, and everything that's further away is colder, and so you end up with a thermal profile that looks like that. And those arrows indicate how much shrinkage takes place, and so that's what causes the distortion. When we do our process, we turn on that induction coil, and it actually heats the metal up to the melting point before the arc comes along, and it heats it very evenly. So we get an equal amount of shrinkage on the top and the bottom, and the end result is the plate sits flat.
Jerry?
Yes.
Someone over in the corner had a question.
Yes.
What's the material thickness in this example?
That is 5/8. Yeah. Yeah. So let's look at the butt joint welding we've done. I got a couple of examples. We were using Hobart Metal Core 6, which has been renamed. It's now FabCore 86R. 3/32 inch wire that we're driving in there at about 680 inches a minute for the 5/8 inch material. 1250 amps. We're using 2 Miller access power supplies. And then we have the 35 kilowatt induction power system out in front of it. On the 3/8 inch material, we were running a little slower. This was one of the earlier ones we did, so we were running a little slower, both on wire feed speed and travel, obviously. And I just stuck these in. I won't spend a lot of time on them, but there's tensile testing for both the 5/8 and the 3/8 material. These are Sharpie tests that we did, and we did both the ones that would meet the American Bureau of Shipping, which is very similar to the AWS D11 code, and then we also did the Naval Sea Systems. Yeah, the Naval Sea Systems ones, and they require very low temperature Sharpie, so we have to go down to minus 40 degrees with these, and in every case we more than met all of the requirements. This should look familiar to you, Jesse, because he did a lot of these tests for us. So both on the 5/8 and the 3/8, we met both the NAVC and the ABS or AWS. That's what our weld shape looked like. Almost almost parallel sides, top to bottom on the 5/8, and similarly on the 3/8 material. Bend tests went fine, and then I get to the distortion, and so we did distortion measurement here on the 5/8 material. Over 8.9 inches, we got 1/78 of an inch of deflection. So it's pretty much as close to flat. Oh, we have a microphone. It's pretty much as close to flat as we can get. Thanks, Bob.
Everybody in the back, good?
All right.
Now, start from the beginning and do it over.
All right. Wait, I've forgotten. On the 3/8, I wanted to compare it to, so the Navy asked us to use SpinArc as a benchmark because that's the process they're using for these thick steels. So you'll see here the top is the submerged arc weld and the bottom is our high deposition weld. In the longitudinal dimension, the top picture, the top diagram in each one of those pictures, that's about a 4-foot section, and the subarc raised up about 5/8 of an inch on each end, and in the longitudinal dimension we didn't see any distortion. Nothing was measurable. In the bottom, we over about a 8.1 inch section, we got 0.02 inches of deflection with the high depth process, and we got almost 1/10 of an inch of deflection with the subarc process. So that was the benchmark they wanted us to compare to prove that we really were reducing the distortion. Yes?
So based on the gas content that you guys had for your torch, which was 90% argon, 10% carbon, CO2.
Right.
Have you guys ever thought about doing tri-gas for higher heat application?
The primary, most important thing is we have a fairly large liquid pool. We don't want it sloshing around, so we need a very stable spray transfer. With the metal core wires, you can go to a much higher current density and still keep a stable spray transfer. And we tried several different argon CO2 mixtures, but we haven't tried any other gases. So we've gone all the way from basically 10% argon to 90% argon, and the 90% argon gives us the most stable arc and the best results as far as welding. This is a medium carbon steel. It's a marine steel called EH36, but it's cross-referenced to A709 grade 50. So it's a medium strength, medium carbon steel.
So really no need for the helium.
Well, we're working with Praxair to look at some other gas mixtures, but we're not far enough along to really talk about that yet.
Yeah.
Okay, so and for the 3/8 we got pretty good results. We got 73.2% reduction in the distortion, and we got 88% in the 5/8 material. So the Navy was pretty happy about that. So we did a demonstration. We welded 2 8-foot by 20-foot 3/8 inch thick steel plates together, and these are our plates in Lakewood if anybody wants to come and see them. They're completely flat, the whole 20 feet in the longitudinal direction, and in the transverse direction, that's a piece of angle sitting on it, and it lays perfectly flat too. So the next effort was to go into T-fillet joints, and we were concentrating for the Navy on 2 aspects. One was welding the T-stiffeners to the bottom of the panels to make the deck panels, and the other was manufacturing of the T-stiffeners themselves. In the past, they've made T-stiffeners by buying H-beams and cutting them in half, but the problem with that is the top decks of the ship are where all the weapon systems are, and that makes that part of the ship heavy. Well, you don't want a ship that's top heavy because it wants to do this. So when you make T-stiffeners out of an H-beam, you figure out, you engineer what size you want, and then you look on the H-beams and you pick the next size up because you can't ever get the exact size you want. And they still want to save even more by fabricating their own T-stiffeners. So we were looking at both problems for the Navy with this effort. So that's basically the problem we're going after. This is a bunch of heat measurement we did on this one. We weren't as exactly sure about how the heat distribution could reduce the distortion. And so we brought in Jim Dido. He has a company in Ohio that does really good finite element modeling, and they modeled both the electromagnetic field and the thermal profile of the material for us. And so we did a lot of temperature testing on the front side and also on the back side, making welds. And the measured temperature profile with the temperature measurement system is on the left, and the model is on the right. The rise time is perfect. We hit the peak temperature almost exactly, so we feel very, very confident that our models are giving us the right information. That's basically all the math behind it. So I brought along a couple of these little videos so you can see, and I'll go back with this one. We actually heat the material up on the discontinuous member a little bit here. If the T-fillet's like this, we actually heat it up there to get the right heat flow to reduce the distortion. So you watch again, you can see the induction and then the arc down on the bottom. And I've got a little bit better 3D model, so you'll see the heat at this is in cross section. I'll go back and run that again. You see the induction heat at the top, and then the two arcs, one on each side. And we've got that same one in cross section here as it sort of runs down the plate. So there's a whole series of cross sections there, and you'll see it heating, the induction heating up above, and then the arc on the right and the arc on the left as we go through each one of those cross sections as we're moving down the plate. And we used this to figure out exactly where we should put the induction heat to get the heat distribution so that we would essentially zero out the amount of distortion we got. So the fact that we have these models will help us a lot now as we move forward to looking at things like aluminum and other materials, because now instead of having to do 800 welds, which is how much we did, nobody had ever done this process before, so we didn't have any good rules of thumb. So this was a lot of welding engineering, try one thing and try another thing. So from now forward, though, we have these computer models which will help us zero in on one. And we just did one for Bollinger Shipbuilding, welding 4.5 millimeter material for them. And I think we came up with a good procedure in about 10 welds. So we're getting better. So here's a video of the front side, I think. Oh no, I think maybe this is just a picture I have. Yeah, and there's the two-sided welding apparatus for T-fillet joints, and there should be videos here running. Oh, there are. I just have to push the button. There we go. All right, so you're seeing the front side weld here, and it's going to split the screen here in a second and go to a high dynamic range camera. And the interesting thing here, if I can carry this over there with me, is because the metal is up at the melting point, the arc is actually sort of machining its own joint. So you'd like to have a J-groove, that's always perfect, but nobody can ever afford to machine J-grooves. But the arc is actually machining a J-groove that's exactly the right size for that arc, all by itself. So that's kind of one of the neat things we found. We have this camera outside, by the way, if anybody wants to take a look at it. Visible Welding just came out with this camera, and you can see not only the arc, but all the surroundings using this camera. All right. All right, so I just brought this up. That little chart on the bottom, that little red dot in that chart on the bottom right-hand corner shows a typical spacing, 25-inch spacing with 3/8 inch thick deck plate, and that's the Navy allowable, the amount of out of flatness the Navy allows them to hit, which is actually 0.375 inches between those two 25-inch spaced stiffeners, and our distortion instead of 0.0375 or instead of 0.375, we're 0.043, So we're 88.5% less than what the Navy even allows. And right now, they're spending $30 million a year straightening deck. So the current process that they're using isn't even meeting that requirement, and we're 88% better than that requirement. So one more shot there of essentially zero distortion fillet welds. Now I want to move now to mobile remote welding robots, and we have one out here for you to take a look at. So how do you make a mobile remote welding robot? You think of a robot in a car factory making arc welds on safety critical components on a frame or something like that, and a lot of programming time goes into making that robot actually operate. And if you're going to make 200,000 parts with that robot, all of that programming time is worth it. But just to give you an example, the last time Dodge made a changeover in the Neon vehicle to a new model, it cost $2.4 billion to do that in their assembly plant, and half of that cost was programming the robots. Half. So that's the problem with applying robotics to one-of-a-kind or few-of-a-kind applications, is the programming time is just prohibitive unless you're going to make an awful lot of parts. But again, technology is coming along that's very interesting, and what we've developed is a robot that operates remotely but has a human operator controlling it. The human operator sits in a virtual reality cell with a torch that's being tracked by an infrared camera system, and everything that the human does with that torch, the robot arm on the torch does the same thing, but it can be 500 feet away up on a big structure making welds. So now we don't have a person up there doing the weld, so that's one advantage. Handicapped people now can go out in the field and make field welds with this thing, so that's another advantage. But the third advantage is the lightweight torch that a person can carry around all day can't weld very fast. But on the robot, I can put the biggest machine torch out there and weld at 4 times the speed. So by putting this robot in the hands of a skilled welder, I give that person a tool which allows them to increase their productivity by a factor of 4. So what did it take to do that? Well, several things had to be done in order to make that happen. The first thing is we need to be able to tell the welder what size and shape of weld they're making while they're making it. Well, you look at even the best finite element models today, and you put in voltage and wire feed speed and torch angles and so forth, and it cranks for about an hour and a half, and it tells you what shape the weld is. We need something that does that in a few milliseconds, not in an hour and a half. So what we've developed is an artificial neural network-based model that can take that data and tell the welder what size and shape they're welding. And once we do that, we can also tell them whether they're meeting, I'm trying to get the pointer up here, whether they're meeting all of the requirements of that welding code. And so if you'll bear with me just a second here. I brought one of those models along so you can take a look at it. So over here you see all the welding parameters. This actually continues down. There's actually 108 separate engineering parameters that the system is calculating. So depths of penetration, leg lengths, effective throat, and so forth. And the reason there's 108 of them is because we built this software for a lot of different people to use. So the AWS code measures those parameters a certain way. The Naval Sea Systems Command code measures it a different way. The boiler and pressure vessel code measures it a different way. And on top of that, Toyota has a code, Ford has a code, Caterpillar has a code, and so we created the system to calculate all the parameters that all those various codes use. So whatever code you're welding to, this system can verify those parameters, and you see they're all colored green up there, but if the weld goes out of spec, it can tell you instantly that you're not making a weld that's within the spec for that particular code. So just to show you how fast it operates, each one of these parameters down here, voltage, wire feed speed, and so forth, is marked. It's got a little sidebar on it. If I grab this and move it, you can see up there in the graphic that the shape of the weld changes instantaneously. So I'm calculating all those parameters and calculating the shape of the weld as I'm changing that parameter. So we now take that data live with a set of sensors, and we can tell you instantaneously whether that weld is actually the right shape and size and is going to meet the requirements for that welding code. All right, so let me go back to the slides here. We need to make bigger print on these things or get me a new pair of eyes, huh? All right, so we got that part done. The next part we needed to do is basically test it and see how it worked, and we did a lot of measuring to verify it. And then we had to build a virtual reality system that would do that. So the first thing we had to do, and we worked with a company called Natural Point, and now they create quite an interesting tool that can be used for welding applications, but they didn't have one when we first started this. But we can now track the torch and draw it in a virtual reality graphic. And so now the human who's doing this can look at the video coming from the torch or can look at this screen here. And there's some interesting features of this screen that we can do for somebody. So for example, if the welding procedure specification calls for certain set of torch angles, we can draw this little wireframe torch here that moves along with it and showing them exactly what torch angles they should be holding. We can tell them if their contact tip to work distance is, in this case, too far away, and then pop this little arrow up here to tell them to move down a little bit closer. Yes? Uh-oh. Hello? Bob? Did I lose it? Yeah, maybe it does. You're right, it's not working. Yeah. Right, John. I'm not sure this thing is... It may have died because it's batteries. It says Mike.
We're in trouble, Bob.
I'll try and yell louder. Bob, this thing forgot. All right, I'll talk a little bit louder. Another thing we can do, it's a little hard to see unless you look closely, but see, oops, let me go back here. See that little yellow line right there? We can show them how big a leg length they should have on each one of those two plates. So they can see the size of the bead they're making and see if it's going too large or too small. Yeah, Bob?
They're going to get new batteries. I think the batteries went dead on your mic.
Okay.
So let me interrupt. The head honcho at the restaurant wants to know if we can take a quick break while they're trying to get the microphone hooked back up. They need a head count for lunch. How many want a box lunch? $10
box lunch.
What?
$10 box lunch.
Yeah, $10 box lunch, and you get a sandwich, fruit, chips,
1, 2.
and a cookie. And what we thought about the box lunch is you can go there, get the box lunch, pay for it, and then go out here and eat and watch the live demos while you're gnawing on that sandwich. So there's two options. They got a regular sandwich and they got a veggie sandwich. So anybody want a veggie sandwich? One. Okay?
John, 2.
2. Okay? How many, for show of hands, and Marjorie, if you have an account, how many want just a regular sandwich? Okay. Sandwich?
You do that half thing.
Keep your hands up, we need to, because they need to make them up, so. Okay, thank you. They do have a restaurant here. If you just want to sit and have something to eat, you can. Or you can go off-site, McDonald's, whatever. They got these places down the end of the street. Okay. Jerry, they get your mic fixed up?
Not yet,
Okay.
but I'll try and yell louder.
Okay.
All right.
Pretend there's students in your class.
All right. The other thing is there's a little speed line. So right in here, oops, when I push that button, it keeps wanting to go to the next slide. Right down there, you can only see the red one here because they're both sitting on top of each other, but there's a red line and a blue line, and the blue line shows you where you are, and the red line shows you where you should be in terms of keeping up with the right travel speed. So if we do go to the next slide,
So it's basically like
There we
a
go.
welding simulator, almost.
yes, exactly. Yep.
Like flying a drone over Afghanistan?
I think this is far easier. I read on the news the other day, or heard on the news the other day, that some of those guys are flying 4 of them at a time because they can't get enough. They can't get enough pilots. All right, come on. This video doesn't seem to be working. Oh well. Anyway, so at least you know how it works, and you can see it out there because we're actually driving the robot with that system. So I can't get that little video to run here. But the other thing we can do, which is quite nice, and this was of strong interest to the Navy, and we've talked to Caterpillar and some of the larger contractors, and that is that we can produce, as soon as the weld is done, a complete quality control report. Because for every slice through the weld, along the weld, we can tell them exactly what size and shape of weld is being made, and all of those engineering parameters and so forth can be plotted on a plot like this, where it's color-coded, red and yellow and green, so we can see how well the welder was doing in terms of holding the parameter. And this is not only just the welding parameters, but this is all those engineering parameters. So you can plot those and see how the weld was, and you can also create a 3-dimensional image of the weld like that, turn the plates transparent, and color-coded. So if there's a defect in there, and so Tower Automotive started using this product on their frame line for one of the Ford truck frames, and the frame continues on down the line having welds made on it. When it gets to a repair station, it goes over, and the guy in the repair station can bring up this image and look at the weld in 3 dimensions and see where the problem is. This particular one was a weld on we've got a system installed on a line over in Norway that's making the side impact beam that goes underneath the dashboard of a car to protect it from caving in when it gets a side impact on an Audi. And in this particular case, there was a fingerprint on that aluminum part, and you can see they got a lack of penetration defect because of the arc instability that occurred because of the oil that was in that fingerprint. So we can detect those kinds of things with this system in real time, and then we can produce an afterward digital quality control report that allows you to bring up any of these graphs and look at the weld from one end to the other. All right, so I wanted to mention this kind of interesting benefit that we discovered. A lot of heavy fabricators put primer on their steel until it's ready to be fabricated. And then they have to go grind the primer off because it ends up causing porosity and other kinds of defects in it. It turns out that if you're running that induction coil ahead of the welding arc, we're raising the temperature of the surface of that plate to between 1800 and 2000 degrees, and that primer turns into carbon dioxide and water. And so this system actually takes the primer off and completely eliminates all the grinding that they have had to do in the past to get the primer off. Yeah, Newport News Shipyard, which builds the aircraft carriers, the statistic that they told us was that that workman's comp claims from the grinders would be enough to pay for the system. So that's another picture of that system doing some tests. All right, so we took this process and went a little further with it, and we said, okay, what if we take that induction coil and we put a cutting torch behind it instead? What might we be able to do there? And the scientific concept is basically when you're using oxy-fuel cutting, the flame heats the surface of the material up to what they call the auto-ignition temperature. If you're above the auto-ignition temperature and you hit it with oxygen, it immediately turns into iron oxide, and that gives off a lot of heat as that reaction, and that's actually what's doing the cutting. So all you have to do is maintain the surface of the steel at that 1600 degree temperature and then shoot oxygen at it, and it cuts through the material. So the key is how fast can you be heating the surface of the material up to that 1600 degrees. So we started looking at essentially induction oxygen cutting, and so if you look at it, there's really no fuel any longer. The induction coil is doing the heating, and along with the oxygen, we're doing the cutting. And this is basically the equation that covers it. But the important part of this equation is that's a constant. So the time it takes to get to that auto-ignition temperature, that's that little T over there, is a function of how hot you have to get it divided by essentially how much heat you're putting into it. So the heat is that heat flux term down there, which is in how many watts per unit area. And so if we take a look at an oxy-fuel cutting, and we have an application, by the way, for the Navy, I'll show you in a minute. It's kind of a cool application. An acetylene torch is going to give us about 48 million in terms of the heat flux, but that 35 kilowatt induction coil is giving us 1.4 billion watts per square meter. So now this means that we can dramatically speed up the rate at which we can move that cutting system. So that's just that comparison again. So the thing that the Navy wants us to do, everybody knows we have nuclear submarines out there, and doesn't look like this video is going to run either. Darn. Okay, well, the United States has nuclear submarines. I had no idea how many of them we have, but there's a bunch. And we're starting to retire them. The original ones we built after World War II are now being decommissioned, and those things are 40 feet in diameter and about 350 feet long. And the hull is several inches thick steel. The exact thickness is a classified piece of information, so we can't talk about it, but you can imagine how long it takes to cut one of those things up. Right now with oxyacetylene torches, it takes about a year and a half to cut one of these things up. They're behind by 7 right now, so they're about 9 years behind schedule, and they have 47 more. So the question is, could we cut these things up faster? There's another slight problem that they have with these that I'll get to in a minute, and that happens to be that there's a coating on them to keep the submarine from the sonar beam that hits it. keep it from reflecting back. And again, that's classified, but one of the things that's in it is rubber. And so when you try to cut that thick steel, going as slow as you go, the heat spreads out into the surrounding material and billows of black smoke come off of that coating that they're trying to do. So that's the second problem we're trying to solve. So anyway, that's a picture of 2 submarines in dry dock, and here's some pictures of our machine. It's actually going to be mounted onto onto a man lift that has a 3,000-pound lift capacity and an 80-foot boom, and it's kind of a complicated apparatus. You can, if I can get the pointer to show up, you can see the boom is going to hold it up against the side in various positions, both going around the submarine as well as going along the submarine, and we're going to be cutting it into 8-foot by 16-foot pieces, which are as big as their crane can lift. So that's basically the goal. That's what one of those things look like. And here's the problem. There's Puget Sound, and Seattle is right next to Puget Sound, and they're not real happy about pollution there. So all that big black billowing smoke is not allowed in Puget Sound. The reason why we have to cut them in Puget Sound is that little red dot down in the lower left corner is Puget Sound Naval Shipyard, is that the reactor has to start there at Puget Sound Naval Shipyard and follow that blue line on a sea barge and go up the Columbia River, and at the other end of that blue line is the Department of Energy Hanford facility. Those are reactors. So it's a deep trench. I think it's about 180 feet deep, something like that. The reactor core, most of those reactor cores are between 40 and 60 feet in diameter, and that's where they all go to, I would say, die, but they don't ever die. They're going to be there for the next 50,000 years before all the radioactivity is gone from them. A long time. So they basically slice the submarine like a hot dog, where the reactor core is, move the 2 pieces away from it, weld 3-inch thick steel plates on each end, and that is the cask now that the reactor core is inside of, the submarine hull and these pieces, and that's what goes in that trench. So there actually isn't any other good place to cut the submarines up except that spot. So that's why we have to solve the pollution problem. So this is a test that we did cutting some material with this process. That little red circle shows you that's the only smoke we get. So we seem to have solved the problem. And instead of, right now, to get rid of that, they actually have to grind that coating away 9 inches on each side of that cut. And we're going so fast that we only burn the coating about 3/4 of an inch on each side. So we're basically cutting that submarine steel. Our goal is to be able to cut that multi-inch thick steel at about 5 to 7 feet per minute. So that's what we're able to do in our lab right now, and we have a contract to build those machines now to go into the shipyard. So the other thing I wanted to talk about is creating weld distortion. Now we've been talking about how to get rid of weld distortion, but what if you wanted to make something without having to apply any force to it to bend it? So we've been working on a process we call thermal forming, where we use heating and cooling in the right ways to get materials to bend without ever touching them, just the heating and cooling of them. And so we started out using lasers, and that's a little stainless steel tank that we made several years ago for Lockheed Martin, and each of those pieces is actually laser welded together. So we can very precisely form a shape now by using just heating and cooling. And that's actually some work we did for the Navy. When a jet engine sucks in a bird or a rock off the runway gets sucked into the engine, it makes a little ding like that in the compressor blades. And so here we were showing that we could straighten compressor blades using this process. So those are titanium compressor blades. Yes?
Is that testing destructive or non-destructive? I can't quite tell.
Which testing?
The one you were mentioning previously with the heating and cooling.
Oh, it's non-destructive. It's not testing. It's actual forming, bending.
Oh, okay.
Yeah. So this is a problem the Navy has. You remember we talked about it. The deck does this, and you can see the problem there. So this is a robot system that we built to actually take that distortion out of decks. That's before we invented the welding process that hopefully will solve the distortion problem for them. But again, an advanced technology portable robot, because this robot scans the deck and makes up its own program to heat it and cool it in just the right places to bring it back to being flat. And so it's kind of an interesting robot, and the nice thing about it is a lot of people can use it. Nora there is the robot there is at Ingalls Shipbuilding where they make the destroyers, and Nora has MS. So this basically allowed her to have an opportunity to keep working instead of having to get down on her hands and knees with a torch and a water hose and straighten the deck. Yeah.
How long would it take to do like an entire deck?
I'm getting there. Good question. So that's what the machine looks like out there. The interesting thing about it, and again, let's see if we can get this video to run. The shipyard came to us and, this one's not running either. That's the problem when you move it from one computer to another. But what those guys are doing is putting the robot together. So you think about, you go buy a standard off-the-shelf robot, and you go to install it someplace, and it takes several days to do that. The goal the shipyard gave us is that this robot had to be able to be disassembled into 50-pound pieces that could be hand carried down inside the ship and put back together, and it had to come apart in 9 minutes. So that's what these guys are doing. These are the shipyard guys in their first training session. And so that robot system can because the ship has to be welded together and all the distortion in it before we can go down and straighten it. So that's what they're doing there, is going through doing that. And here's a report that was written by Northrop Grumman about the machine. That's a deck that we did in an industrial engineering test, and they had us straightening with the robot. Well, actually, their people, but our robot. And then they had a fellow out there, one of their best straighteners, with a torch, and basically we got our section very straight, and they in a week's time, 40 hours, they did 17 of those, roughly 6 foot by 2 foot rectangles, and we straightened 44 of them. So we were 2.5 times the productivity level, but our system heats and cools so fast that the paint on the other side never gets hot. With a torch, it heats so slowly that there's plenty of time for heat conduction through, and it catches the paint on the back side on fire. So they have to have a second person with a fire extinguisher underneath there. It's called a fire watch. We don't need that. So we actually can straighten the deck 5 times the speed of the manual torch process with this robot. So then after we got the deck plate system running, they had us build one that would do bulkheads. Basically, those are walls, and also hulls. You can see the side of that ship. That's see all the distortion, all the weld distortion, making all those ripples in the side of the ship. And so we're using that same man lift that we're going to use. We have a system now that does also the hulls, so it'll straighten the hulls. But this is probably the most interesting one, and again, I hope this video will run. Let's see if it will. It is running. It's running very slowly, but so we built a system. You remember I talked about the largest, tallest wind towers in the world? We have to bend that steel plate. So we get flat plate delivered, 10-foot by 40-foot sheets of 3/4-inch thick plate, and we have to bend it. And so we have a prototype machine that has 6 induction, 35 kilowatt induction heating heads on it right now. The final machine, assuming we get the investment money and we get it built, will have 74 of those heating heads on it, and we can bend into the shape that we need, a 10-foot by 40-foot, 3/4-inch thick steel plate in that 15-minute cycle time that we have to do it. I have a couple other pictures. That's what we've got about a 1/4 mile long portable assembly line out in Oklahoma, and inside that old barn is the forming system, and you can see the kind of bends that we're getting in that plate. It's actually corrugated, so we do a reverse bend here and then a forward bend there, maybe a little close up there. So that's what we're doing to that 3/4-inch thick steel plate with that thermal forming technology. So that's what we're doing with portable robots there. Now, finally, this is the one that we have out here for you to take a look at. Those little circles on there, the right-hand green circle is what we call a nanny cam, just a standard camera, and that's what the person uses to drive the robot to where it's going to go. It's a crawler system that's built by Robotic Technologies of Tennessee, like a little bulldozer with tracks on it, except they're magnetic. So it can crawl up a steel wall. It can hang upside down. It can carry about 150 pounds, and it can travel at about 130 to 140 inches a minute. So we put a big heavy-duty machine torch on there, and we can weld at speeds of 140 inches a minute with this thing. It also, there's where the arc is, and the left hand of the green circles is that high dynamic range camera. So the person who's driving it can see the arc and all the surroundings around the arc much better than they would be able to see if they were wearing a helmet, for example. And John there, as you can see, he's not looking at where the weld is. He's looking at the virtual reality screen, and he's holding the portable torch. And like I said, you'll be able to see this thing operating at noon today. So that's what the screens look like. The bottom screen that he sees is the camera image. The top screen is where the virtual reality is. That's what the robot looks like. So this part is the magnetic crawler. On this particular one, we had a 6-axis arm. On this one, we have a small 4-axis arm. It carries its own wire feeder, or it can feed from a stack pack. So if the stack pack is on the ground with a push-pull feeder system, we can put a 600-pound stack pack of wire on this robot, and it can crawl around on the side of a large steel structure and weld all day long, basically. So that's what it looks like, and that's another video. Let's see if it'll run. It doesn't, so you'll have to watch it at lunchtime. And it makes pretty good welds, actually. We call it a cobot. NASDAQ now actually has an index for cobots. That's collaborative human-machine systems or robot systems, and that index grew by 500% in this last year. So collaborative human-machine robots are actually taking off worldwide in terms of where they're going, and we think it should be applied to welding too. So, thanks for your attention. Questions?
Back to your welding process. Several questions. Do you have to develop welding procedure specifications, and which codes do you have? Several codes you do it to?
Well, right now, everything we're doing is for the Navy. We are talking to several large fabricators who are interested in using it in other applications. Most of them are actually using A709 grade 50, which is exactly the same as the EH36 marine steel that we've been using, but we will be developing procedures for them. So just like any other welding process, you'll have to develop a WPS, get it approved, and to be able to qualified. Yeah.
And the people that operate it, are they welding operators or welders?
Well, it's a robotic process, because the induction coil and all that stuff is way too heavy to carry around. So it's not a manual process, it's a robotic process. So, you don't really qualify a robotic operator, but you qualify a robotic welding procedure for that robot system.
But if you have humans operating, do they have to be qualified like welding operators?
Well, in this case, we're not. It's just the robot running it. So it's just.
Yes.
Yes.
You can't get
You
the
do?
janitor to do it and then let Jerry do it.
Oh, I see.
But
Okay.
person-
All right.
Person, yes.
Then I stand corrected. Jesse's the guy.
And then what kind of inspection process do you have to use? Is it do it, like you said, itself, or do you have to have an independent inspection?
Depends on the code. So for the Naval Sea Systems Command, in some safety critical welds, they do radiography. Other ones, they just do maybe dye penetrant or mag particle. Other ones, they may just do a visual inspection, but we can give them a real-time quality control report as well. We're not to the point where anybody's going to accept that yet. There's still got to be a lot of work to do through organizations like D11 and so forth to get that done. But in the process, we're going to be installing a system at Bollinger Shipyard, which is going to be welding Coast Guard, the new Coast Guard ships. And we're going to go through that whole process with NAVSEA. And so hopefully that will carry over now, and we can prove to D1.1 that the process can be qualified, and that the electronics and software that we have for it can be used. But that's a whole process. Like I said, they won't even give it a name until we have the first one actually in production. So we have to go that next step. So this next year we'll be building a system and installing it at Bollinger Shipyard down in Lockport, Louisiana. Yeah. Are we out of time?
Yeah, we're getting close.
Okay.
We've got a question.
We got a couple questions if we can do it.
Lifespan on your heating element that heats the core well.
It's just a piece of copper, water-cooled copper, so it's good. But we actually concentrate the electromagnetic field with something called a flux concentrator, and they do have to be periodically replaced. But it's once every 6 weeks or something like that.
How big
Yeah.
can you go on your butt welds?
Well, you're going to see a presentation a little bit later on by Eric from Weld Revolution, and we just put in a proposal to DOE to start looking at welding the containment vessels for their new nuclear reactors, and so I think we're looking at 3.5 to 6 inch thick material there, but we'll be developing the procedure. So the coil's going to have to go down in the joint. Right now he's welding 3/4 out here, single pass, but he's going to have to modify his torch so we can go down in the joint with it. But that's the goal, is to be able to weld without a V-notch. Weld 6 inch thick material, single pass, or not single pass, but it'll be multi-pass, but no joint preparation.
One more quick question. Is there any hardness testing on your flame cutters?
Actually, Chicago Bridge and Iron is starting to do that right now. The Navy didn't require it. All they required was tensile tests and Sharpie
So
tests.
you don't have any idea when you're coming up with?
Nope, but I'll know probably in a month.
Okay,
All right.
well, let's take a quick break. I think that coffee's kind of, oh, Jesse's got one thing for
I
you.
want to make a quick comment.
Yeah.
This symposium is entitled New Technology in Welding. This is our keynote speaker. Quality of these presentations meets or exceeds the quality of the professional development program presentation
Just set it
that
down.
you would experience at the AWS exposition in Chicago, Las Vegas, Atlanta, wherever. So we are very, very fortunate to be able to do this right here in our hometown. The gentleman, the questions that he asked, all of it, in the spirit of certified welding inspector. We all know a certified welding inspector cannot inspect a weld without a drawing and a welding symbol. That's it. Welding, design, material, process, quality, safety. We all know those 5 aspects. As you're sitting here today, the skills that are being, we'd like to encourage in your head, knowledge and skills for the inspector how to prepare a report, communicate effectively, the fundamentals, understand the fundamentals, and the welding symbols and drawings. Inspection standards, verify the base material, filler metal, shielding gas, drawings, documentation, inspection, verify welding equipment compliance, joint geometry compliance to the welding procedure, inspection for verify production welding, visual examination, quality and safety, perform audits and surveillance. So as I was looking at this, and I'd like to encourage each and every one of you, as you're looking at these presentations, of course they're over our head. I don't understand it either. It's new technology. But I tell you what I do understand is I understand inspection. I understand audits. And as I look at these things, and Jerry, how would I write that up? If I had to make a welding plan, inspection plan, how would I do that? These are things I can think about, and you very aptly brought that to all our attention. How we need a welding procedure. We need operators. So I share that with you from my point of view. So carry on.
Okay, we're going to take a quick break right now. The restrooms are right down the hall, and if anybody needs anything, there's some machines out there too. So come back, we'll get to start the next presentation. Has everybody signed in? We got a few sign-in sheets here. If anybody came in a little late, please come up here and sign in, please.
During the lunch demonstration. During the lunch demonstration.
It was on the internet. Well, it might have been a post office.
Well, I don't need it that bad. Not bad enough to make a trip hazard. I can. Okay. Yeah, because I have one left. Okay. I'll just recharge up during break and then move it back. Okay. Yeah. Do you have a jump drive?
I do. Each presentation on there is one of the awesome ones. Yeah. I'm going next. I don't think so.
We're running over this laptop.
Yeah.
So when it's like that one's on, do you have a little port that I could put this on?
It doesn't have QuickTime is why some of his videos weren't playing. Yeah, I saw a tiny little blurb on there that said it didn't have QuickTime. Now I only have 3 videos. I'm not sure if any of them are QuickTime, but if you want to download a QuickTime driver, that might help.
I'm surprised it doesn't. So is my presentation's on there?
This is your jump drive, right?
Yeah, that's another one. Yep.
Your power presentation.
Okay, so we're there. Good. I'm not presenting yet, so okay, I'm up next. Can we check this while we're here? Let's check this real quick and see if that video is going to...
Because we're broadcasting these out on AWS.
Just make sure that'll work.
Yeah.
And we have sound and everything.
Yeah, I'm at 2.
I don't know if we actually have sound on that.
All right.
Nope, no sound.
Yeah. I just hope not to put people to sleep. That's
Maxed.
my challenge.
I think this is,
I don't know.
I think it's a good,
I don't see a... Well, no, that's your power cord.
Yeah, no, there's no sound to.
Yeah. I noticed a little pop-up that came up.
They've got to have sound in here somewhere. I know they do.
That was one thing.
Mark, you don't have QuickTime. That's how we read it.
Yeah.
Okay.
How about this? What if we do this?
You drop in and you never get a chance.
Well, experienced
when we go through the mic.
Yet there are few ways to recruit, screen, and train
just set that
students and
next to the speaker
operators
on the
that deliver the impact you need.
See if that'll work.
Introducing the LiveArc Welding Performance Management System. A revolutionary, reality-based training solution from Miller that offers exactly what you're looking for. Once you know what this system can do for you, you'll understand why
I can't tell who your speaker is.
we build careers. LiveArc is an advanced weld trainer that combines the benefits of a simulator with the advantages of LiveArc welding.
That'll work.
In a single,
Okay.
easy-to-use
Put it
system.
straight there.
Personal instruction is essential, but have you ever wished that your trainees could receive immediate, objective feedback, even
Well, that's a good question. And we are working on practice for all kinds of different aspects.
So I've known that even with like even TIG, helium, and argon, you can take that 200.
It's not heavy.
Now we're not responding.
Sure. So I figured
what's going on.
Well, that's kind of what I figured I'd do.
that would be
I've been depending a lot on the experts.
Tried to close it out once already.
To help us with that. One thing we have done is they have a new gas composition that they've just introduced this last year, which adds a little bit of carbon tetrachloride to the gas mixture, just a trace amount. But what it does is the chlorine reacts with all the monatomic hydrogen.
See what's going on up there?
Gets all the hydrogen. So we're looking at the possibility of low hydrogen welds with that gas in our process.
You're right.
Welds fails, yeah.
Live stream. No big deal.
especially with and know for just because going with those kind of welds.
Most of the stuff that goes with
Good, yourself?
It's pretty good.
Doing all right.
Are we using our own PCs?
No, we're on here, so we'll need a jump drive with. There, do you have a jump drive?
I don't have it on me right now. I have it saved on my computer.
Okay.
In my, I'll do it during lunch. I'll get it all set up.
Okay.
Make sure, because I have a video that I'm on and just want to make sure that works.
we have a project.
I brought a computer just in case I wasn't sure.
You need sound? That's fine. I just wanted to make sure, so we're good. Speaker's right there. Okay.
Yeah,
Chemistry such that they have
because we're doing a live stream.
they think they can
Are you streaming where?
We're streaming live on YouTube.
Oh,
So I'm actually have to recheck it and make sure we're back there. So we can't switch to a different computer or.
no, that's fine. I just brought it just in case, but I can pull it off. I just wanted to make sure my video works.
And we have jump drives around. So
you say, well, yeah, I feel Linda's
we can make sure we get all of it.
to make the stuff in sheets, so we can put it on a roller. Contact it's not quite clear. It's actually switch the light. So
when you're doing the laser bending,
yeah, it's just me, Cheryl, right?
perfect.
Oh,
Actually, aluminum
and then
stainless. They have
after steel.
higher thermal conduction, so it's working even better.
Yeah, but the whole key is,
I'm not up there.
what we have to do, what happens is you heat the surface.
Oh, are you?
I
think so.
Down into a spread.
Who's up next?
Then that section is constrained, and the only thing you can do
Colorado School of Mines.
is pick it up and it permanently changes shape
Test your videos if you want.
at a time when it's straight.
So,
Left analysis, left button work.
It starts to
This one?
pull back down and strength starts
This
to
one?
come back up. And now it starts to
There's a company video. And
So the key is, and so.
we have volume.
The mic will have to do the volume.
Okay.
Process that allows you to perform superior welds while
Now, how do I
improving
shut it
efficiency.
down?
This patented technology has an adjustable rotating welding arc, which enables welding in all positions, using both solid and metal core wires in a spray-like mode.
How do I get
Our
full
rotating
video?
arc technology can be used in all welding positions due to the surface tension created from the high-speed rotation. Joint preparation can be drastically reduced, as a square-cut edge is sufficient for most
do I get
welding
out of this?
applications. By minimizing beveling, weld stress and distortion are reduced. The high-speed revolving motion holds the pedal of the joint, and the stirring action results in a
And they make weird shaped buildings all over the world. It's
That's the problem.
Weld Revolution has created a unique weld.
Can I go back to presentation?
You should be able to click on that.
Okay.
And then that's when it should work.
a very expensive framework, and then they put sheet.
I just want to make sure I can come in and out of these videos.
To make the metal
I got it.
shape of thick material and make it the actual frame itself, no frame. So
Do it one more time, just make sure I got it.
they use so we've got two big
And where we're getting audio is through their mic to that corner, just like that. So the audio on the broadcast through there. Okay.
you do that. The real thin material, maybe to go to laser, but it's a lot.
Back there. Now, if I want to go, that's forward. How about backwards?
I'm
What
not
I'm
sure.
gonna do is,
Maybe back to
Oh, there we go.
So you can use those
Those
like
arrow keys.
Yeah.
Okay, good.
Oh, carbonic. Oh, I cool.
Oh wow, I'm going to talk a little bit about cladding.
You are?
Yeah.
Well, we have game-changing technology for cladding. We'll talk about some dilution levels
Oh, okay.
below 2%, half a millimeter from the bond line on 625.
Get the bowl shape.
2%, half a millimeter from the
Less than
line.
2%, half a millimeter from the bond line.
And so we have two different methods.
Carbon
We call,
content.
we call one.
Okay.
Iron content.
Okay. Cool. Yeah. I've just barely started doing some of that chemical analysis close to the bond line because I'm comparing
But not let it
solid
spread.
state friction welding for cladding applications. And then I did cladding myself with a few different processes, flux cores, to compare fusion welding.
We actually started to grow.
So just flux core arc welding, a 309,
So we can actually take
and
the
shielded
material
metal
out.
arc shielded metal arc welding. This is stick welding.
Is that your presentation?
Yeah, it's in my presentation. Yeah, some of that chemical, a little bit of that chemical analysis. Yeah.
Make a bad weld faster.
That's right.
If it's making a bad weld, all it's going to do for you is make it faster.
Make bad welds faster.
And yeah, more of it. So, yeah, this is the, oh, it's not up there now, but basically that was the screen that's doing the broadcasting or the streaming. And so with that, he probably didn't want to hit enable, probably. Okay. So, Andrew Neill.
All right. Thank you, everyone.
Mark?
I don't know why. Sorry.
So in my presentation today, I'm going to talk about my research, which is observing the weld pool in 3D. So I'll talk about some of my work as well as the state of the art. As Jerry said, I'm a PhD research student at Colorado School of Mines. I also work at Wolf Robotics, so all of this is very near and dear to me in that I really want to get a smarter welding robot. And really the core issue is that robots are blind, deaf, and dumb. They have no idea what's actually going on in front of them. You program in a bunch of points. It's very similar to a CNC machine. You have to give it a list of commands, move from point A to point B to point C, start welding at point B, stop welding at point C, things like that. And there's no information going back into the controller. There is a very limited amount of waveform data like voltage and current that it watches, but it doesn't actually
Go
under view, far right, up, there, view, and then look at the view.
it should be in presentation.